Good morning, everyone. Today is April 21st, and this is the John Chappell Natural Science Philosophy Science Chat. We have this on basically a weekly basis. Please come visit our website, naturalphilosophy.org, and you can join our membership, get on our email list, participate in our forums and our wiki, and we also can be found on Facebook. Our next conference is coming up very shortly in June 27th to 30th in Connecticut, calling that the Critical Thinkers Conference at the University of Connecticut. And I've been doing some research on accommodation, so one possibility, if you'd like to stay at the conference site itself, are the economy dorm accommodations, which will be $69 a night plus tax per person. So I'm thinking really hard about going to the conference. I think I probably will. I just need to go buy some airline tickets and make some accommodations. Okay, so let's see who we got here. Okay, we got a couple people here today. So today is an open forum. Last week we had Ian Cohen with us discussing magnetic waves. And so I want to first open it up for if anyone has any topics they'd like to discuss this week. Anything that you saw in the news or anything that you saw in coming across the emails that you thought might be interesting to discuss. Perhaps, Harry, you've got something. You always have something on your mind. We've got some other people here. Who do we have on the phone here? 4271. Yeah, we hear you. You guys have, and we've got someone from Hungary. All right. Well, if there's nothing that you guys wanted to discuss particular, I'm going to take my cue from Glenn Baxter, passed away a while ago. And what he would
today? Do. Is Ian here?
Ian? No, Ian said he couldn't make it here today.
Okay.
Then I'm going to take a page out of the Glenn Baxter playbook, and what he would do, he would pick a topic and have a list of things to discuss.
Please not let us argue about the atom again and the structure of the atom.
Well, that's actually the topic that I still have, because I still have the very large list that I got from Bill Lucas of all the things that...
Is Bill Lucas here?
No, I don't think he's here. So, but there's all kinds of atomic data that you can look at and discuss. So what, Harry, are you getting tired of talking about atoms?
Well, I don't really see what it accomplishes.
Well, first of all, do you think science understands how atoms work?
That's a kind of a loaded question. You would have to sort of specify in particular what you mean by that statement. That's so vague and ill-defined, it could be interpreted any way you want.
Okay, how about the specific
if you were to ask me, does science work, I would say no. I don't think science has a method that works correctly, so I can't really believe anything they tell me is true because they say so. So that's another issue. So what issue would you like to focus on?
I would like to focus on the specific construction of the atom. What is it made out of, and what does it geometrically look like?
We already know that. There's not any argument about that.
Okay, so what is the
You're the only person that's arguing about it. I don't think anybody else is. So you're kind of alone in the wilderness on that topic.
Well, that's possible. I mean, what is the mainstream conception of the atom then? right? So what is the known thing that everybody accepts?
You're the moderator.
Yeah, but I obviously cannot unbiasedly represent the mainstream position because I disagree with it,
Well,
right? So
you
there wouldn't be
object
any
to
point
the
in me.
idea that there's a nucleus and electrons orbiting the nucleus. And I don't know how many times Bill Lucas has explained that experimentally that's shown to be correct. I mean, he's gone over that a number of times, and every time you bring that up, he refutes it. So I don't really see any point of discussing this anymore.
Well,
Quite
actually,
frankly.
that would be strange because the one thing that Bill Lucas says is that an electron cannot possibly be orbiting a nucleus. That is one of the things that he definitely says. And his own model shows the electrons in static
Okay, so I correct
relationship
that.
to
The
the
word
nucleus.
orbiting is correct, outside of the nucleus.
No, Bill Lucas would totally deny that.
Okay.
I
Well, not
mean,
here. I don't
if
know
you
what
look
his
at his common
position is
sense website,
exactly.
if you look at his
You're
common
just
sense
making up
website,
stuff, Franklin, like
no,
you
I'm just,
usually do.
I am just pointing out
Bill
that
does say that
not
the Bill does, does say that the electrons maintain fixed positions within the atom. The thing is that it depends on the atom, because if it's just a hydrogen atom with a single electron, electron, then that electron would necessarily orbit the nucleus. But if you had an atom with two electrons, then those electrons would still circulate, because Bill does have a circulating toroidal shape atom. Those electron field patterns would circulate, but they would circulate like on opposite sides of the atom, since their electrical characteristics would repel each other. And so you'd wind up kind of like with a dumbbell like looking atom with the electrons themselves would still be circulating. They just wouldn't be circulating the nucleus anymore. And that's kind of how I perceive how Bill is demonstrating his. And because the electrons are circulating, the electron pattern is circulating, Bill utilizes the magnetic field, basically alignments of the magnets, to determine the interconnection or the position of the electrons within the atom. And I think that's he and his son. I don't know how much, I didn't quite understand exactly how much his son had to input into that, or if he and his son worked on it. But that's kind of where they came up with it, from what I understand of this model. Now, Bill isn't here to explain it all, but so I think in a single atom, like a hydrogen atom, where there is no opposing electron to push the electrons to either side or to a different location outside the surrounding the nucleus, that case, the electron pattern could be encircling the entire atom or nucleus. That's my kind of take on it. But again, Bill's not here to really answer that question, so I don't know if there's much point in speculating more on his atom.
well, I think he definitely believes in the toroidal electron ring model. So that's the circulation that's going on here. But clearly he will always bring up his son's science fair project where he suspended the magnetic rings, and you can show that they kind of form a stable structure if you put them in the right way. But quite clearly, Bill also has a very different conception of the atomic model than mainstream. He definitely doesn't accept he would disagree with that. I mean, I disagree with the mainstream model on a number of different grounds. I mean, the largest being that there is no tiny nucleus made out of protons.
Well, there's no evidence to support that, so I don't really think we ought to discuss that further. I mean, that's just an erroneous concept that you're flogging based on no information at all whatsoever to support your point of view. So I don't see any point in continuing on in this discussion.
Well, what happens if it's correct?
Well, I think the advantage
to, not mine.
I think the advantage to Bill's model is it explains things through the magnetic field, which, we all, I think most of us understand that, magnetic fields and circulating electrical patterns are always working together. And so if he has electrons circulating like they do in the toroidal ring, that gives it a polarity, which makes it, more polarizable like a north-south magnetic pole. So I think his model and explanation kind of demonstrates that. I think the model we see quite often of the boron atom with the electron paths circulating in different planes or in different directions, almost in the same plane, is probably the model that Bill opposes, and that makes sense to me that would be opposed because the magnetic fields would not align in such a way, and certainly if they're circulating electrical pattern, there's a magnetic field generated, and they wouldn't create a pattern that would circulate uh, like the atoms. Like I said, the images we often see, and I don't know why I can't pop one up right away, but I believe you probably all know which one I'm kind of talking about, where there's just kind of a cloud or almost a cloud-looking characteristic to it, where the atoms, the electrons, if there's 5 electrons, are all orbiting in different planes that are, 1/5 of the 360 degrees away from each other. Something, and that really doesn't logically fit too well. And I think that's what Bill argues against.
Yeah, I think that's what we're all looking at. Where we're looking at that the current explanation doesn't hang together too well logically. Now here's another thing. Now, if the electron is like freely orbiting the say the proton in a hydrogen atom, then you would expect that the electron would not necessarily closely follow the electron. Now, can you guys see the screen I'm sharing here? This is a new experiment where they're independently tracking the proton and the electron. And, they're kind of jiggling it around. And what they're finding is that the electron and the proton are following each other. And it's a lot closer than you would think it would be because the mass of the nucleus is 1,800 times more than the electron. So
could you move the image down a bit or something? Your picture is covering the top part of it there.
Okay, well, I think I just moved it down. Like I said, can you see it now? My connection is a little bit slow, so it might take some time.
No, not really.
Okay, it might take some time for that to move down. I just scrolled it.
Let's see if I can do something to my screen. No, nothing I can do here to change it, but I can't quite see it. Go ahead.
That's okay. It's just a picture. And it's a little bit hard to see what they're trying to display here, but that's just the experiment. But the conclusion that they came up with is that the electron, the position of the electron and the position of the proton in these hydrogen atoms is highly correlated. So wherever you see the electron, you see the proton going right with it. So the question is, how do you explain that in terms of, say, the mainstream idea where the electron is not really attached to the proton? You'd think that, well, the electron should be able to go just about anywhere, and the nucleus being so much heavier would probably always be lagging, or at least certainly not be in the same spot as the electron moves. So that is a contradiction, and that's why we need to look at these questions.
Contradiction? That's just your opinion that it's a contradiction. I don't see a contradiction. The electric attraction between the proton and the electron caused them to move together. Where is there a contradiction?
Well, the contradiction is that the proton is 1,800 times more massive than the electron. So the electron should be much freer to move around than the proton itself. We should be able to see the proton like just about anywhere, while the proton is just sort of kind of stuck in the middle. But this experiment doesn't seem to show that.
Well, you obviously don't understand this experiment, so you're just trying to make up stuff based on an experiment you don't understand.
Well,
I think what the experiment is showing is under an electric field when the atom is accelerated, the electron leads the proton, the nucleus, through the field. So there's kind of because the electron is what's first affected by the electric field, and so the electron is being pulled forward towards the target, and the neutron, the nucleus, which is the heavier proton, is being dragged behind because the electron and the proton are attracted to each other. But it's actually the electric field is actually affecting more on the electron, which is the outer shell, more towards the field's change. And so I think that's what that's really showing. It's not showing that the electron and proton are circulating outside of a center point. The proton is still the center point in the nucleus of the atom. And of course, the proportions, it can't be right on the screen because you just can't draw anything to that scale and still be able to see it or demonstrate it. So the proportions don't mean much. But the title right there says, nuclei catch up with electrons. So as the object or the atom is accelerating towards the screen, the electrons are being drugged first by the field, and then the proton is being drugged by the electron's field. That's the way I read that.
Well, here's the specific quote inside the article. It says, in these studies, the dynamics of the nuclei around which the electrons evolve is assumed to be frozen, given that the nuclei are much heavier than electrons, and therefore move more slowly. However, even in the attosecond time regime, the approximation that that electronic and nuclear motion are decoupled from one another is often unjustified. In particular, in molecules composed of light atomic species, the nuclear motion can be as fast as electron dynamics, resulting in a strong coupling between the two. So that is what the researchers say.
So what does that mean?
What does it mean? I mean, they were saying that they expect that the nuclei be basically frozen, given that they are much heavier, and they expect that the nuclei would therefore move more slowly. Do you understand that? I mean, that seems pretty clear. I mean, I just about worded from the article. They expect the proton to move more slowly. I mean, that makes logical sense, right? But that is not what they observe. That they're saying that there's a very strong coupling, stronger than they expect, between the electron and the proton. That the proton is moving as fast as the electron.
Well, the only time that there would be a decoupling is during the acceleration period. Once you're at coasting speed, then they would be both combined and caught up with each other. It's like towing a heavy vehicle with a light vehicle and a spring in between. Once you reach coasting speed, that spring is going to contract and you're going to get down to your normal distances between them again.
Well, that doesn't seem to be what the experimenters are concluding here. Now, they're doing things which they're trying to just barely ionize the electron off of the atom. But, so they're trying to bounce the electron around without actually separating it. But I think they were expecting to observe the electron.
Why are we talking about this? What's the point of this discussion? I don't really see that this is going to lead us anywhere. I mean, basically, we're talking about an experiment. We don't know what they did, and we don't know how they did it. And you're talking about it. If you want to talk about this experiment, give us a presentation on all the details of what they did. This is nothing more than, a news release. And a news release doesn't tell you all the details about how the experiment was conducted. And, so they give you this little paragraph at the end that they say this is blah, blah, blah. And it's mostly designed to get people's attention. Okay. So I don't think doing science by news articles is really, worth anything. So why are we talking about this?
Because I don't believe that's true.
Nobody else is
absolutely
bringing
not
anything
true.
else up, Harry. Have you got
don't
something
believe
to talk
what's
about,
true.
Harry? Have you got something to talk about, Harry?
I mean, my job as a
Lots of things
moderator
to
here
talk
is
about,
to find things
but
that are
we can talk about lots of things, but why are we talking about something that we don't understand what it is?
We're trying to interpret it. We're trying to we come up with an understanding. If you would like to, you could research it for next week and present your findings, Harry.
Why are we talking about some experiment that he picked out of some kind of news release that we don't understand? I mean,
because nobody else has come up with anything else, Harry.
And right. it's a new result. It's a brand new result. So if you're interested in experiments, this is a new result which contradicts the known
That's your claim that it contradicts. How do you know it contradicts anything?
I just read the paragraph that the researchers.
It didn't sound like it contradicted anything to me.
Well, I don't know how you can think that, because it says that. See, directly it says here that the approximation that the electronic and nuclear motion are decoupled from each another is often unjustified. So that is the current approximation, that they would expect that the heavy nuclei would not move as fast as the electron.
To me, that just says that the model that is sometimes used is in this particular instant unjustified.
That's right.
All he's saying. He's just saying we found that a different model can be used in this particular experiment that isn't used in some other types of experiments. So I don't really see that implies a contradiction. That just implies, that this particular experiment uses a different type of model than other types of experiments do. So I don't see that justifies the idea of a contradiction.
That is the definition of a contradiction. You have an experiment that denies a particular model, that contradicts that model. I
think you're out to lunch, Franklin.
Well, what do other people think? To me, that's perfectly sensible. I'm absolutely just floored that Harry just cannot understand this is pretty clear.
You're making a claim based on an article that you picked out of no place, which on my mind, I don't really know what it was that they did, because the picture doesn't tell me anything. This is just a news article that doesn't really tell us anything. So why are you picking on this particular news article? Because you think it creates a contradiction.
It doesn't create a contradiction. I'm not the one who's making the conclusions. You can read for yourself from the researchers.
The way you're reading it isn't what I read it. You're saying you think it means one thing. I think it means something else. So I don't think that's really the basis for having an argument of a discussion of any that can lead anywhere. Your interpretation of what this says is one thing. My interpretation is something else.
What's your interpretation, Harry?
I have no idea what they're talking about.
Oh, okay. Well, that's a hell of an interpretation, Harry. That's very useful.
Well, since I can't agree with anything that Franklin says. Does Franklin understand it?
You certainly can't disagree either. You don't have an opinion, you said.
Well, I heard what he said they said, and it didn't sound like what Franklin thought they said.
Your only opinion.
I don't know what they're saying exactly.
Franklin doesn't know what he's talking about, even though you don't have no idea what it is.
What I know is I don't think that talking about this experiment is going to be very fruitful for us.
Well, I think we need to bring in a neutral third party here.
Explain to me why talking about Franklin. Explain to me why talking about this experiment has any meaningfulness.
Because it shows that the current atomic model is wrong.
No, that's not what it says, Franklin. They didn't come out and say that. Where in this paragraph in this news article did they say the current atomic model is wrong? Where did they say that?
Are decoupled from another is often unjustified.
That's not saying the current atomic model is wrong.
Yes, it is saying the current model, current atomic
Well,
model is
I don't know.
wrong.
Your apparently use of the English language is a lot different than mine.
The word unjustified, that means wrong.
No, that's not what it means.
That's exactly what it means.
No, that's your impression of what it means.
Well, gentlemen, I'm going to have to go clean some ditches, I think. I think it'll be more fruitful than this.
Quite possibly.
Oh,
No, I think we need to get some
by the
other
way,
opinions out here.
by the
So
way,
I'm going to call on Mitch. Mitch,
3.44
what do you
billion
think of
people can
this
fit into
controversy
34
here?
by
Well, I
36
think
by
until
36 square mile area. Bye. I'll listen.
Okay, thanks,
Mitch.
Cornelius.
I
So
for,
Mitch,
I'll
what do you
listen to
think?
I'll listen to Mitch here. Thank you, Mitch.
thanks. I think until we find another topic, I think this is kind of interesting. I'm not particularly into their particular results, but until we find another topic, it does seem a little interesting. But my own views, I don't know if I can really. I argue with the whole atomic model myself. I don't believe is right, and I'm a lot like you, frankly, in the respect that as far as the nucleus goes, I don't think. My own opinion is the nucleus isn't just a bunch of nuclei stuck together in one static place. I believe in a dynamic nucleus myself, much like well, if you only have like hydrogen is static, there's only one nucleon, but let's say H2, for instance. I believe that H2 it would be kind of like a binary pair. They revolve around each other. When you start getting to larger atoms, I believe that it's like a multi-body orbitals. I believe that the nucleons actually orbit each other, just like the electrons, or a lot of people believe the electrons encircle further outside of the nucleus. I just like Glenn Borchardt says, everything is in motion. And I don't believe that the nuclei is just a bunch of nucleons stuck together in a place like most people see that. I believe that it's
Yeah, but
dynamic.
Mitch, I don't think that's what mainstream says.
So mainstream does allow that there's a possibility that the nuclei do orbit each other also?
I don't think the word orbit is correct. I think that if you look at what Hans von Leunen is saying, he's saying that the nucleons and the particles are basically in a kind of statistical motion, okay, if you will.
Okay.
All right. Now, to use the word orbit, I think is misleading, but that's the common word that people use. I used it incorrectly, but there's motion involved. The actual type of motion involved is essentially not exactly clear in the sense that you can't actually pin down the motion and say it's, we can track the trajectory of the object that's moving and it moves in a certain well-defined deterministic trajectory.
Okay. Well, thanks. Yeah, I didn't realize that. But my own views still do differ in the fact that I do think that the nuclei orbit each other in kind of a multi-body type orbits.
Well, that's an interesting idea. There's lots of different ideas about this. What actually happens in the nucleus, but I don't think that you have like a mainstream, they show you these models in chemistry where they show these, things stuck together and of course the model doesn't, it's just an illustration. It's not an actual literal interpretation of what's happening.
Okay. You have to read up on that a little bit more.
Yeah, it's just a quantization model to give you a clue for how much energy is in the nucleus, and more about the packetization of it than a physical model. It's kind of what you're saying too, right, Harry? I mean, it really doesn't tell you what the real arrangement is, and like even Bill Lucas says that there's no evidence for the individual neutron inside of an atom is what his opinion is too, and I'm kind of in the agreement too that the amounts of energies are there in a nucleus, but they're not small little chunks of energy that are glued next to each other or anything like that that you see in images. And I don't believe, like you, Harry, I don't believe that mainstream is trying to tell us that that's a physical arrangement of protons and neutrons within the nucleus is understood. What arrangement there is, I don't think they have an understanding of that, and I don't think they declare there is a particular one. But it does show those images in your chemistry books and that, but it's more for an accounting type purpose than anything else.
Okay. Yeah, thanks about that. And I guess maybe I'll throw this out there just in case it sparks maybe a topic that could be discussed. I also think that it's a possibility. We all know the experiment, the gold foil experiment. I don't believe in
the what experiment?
Oh, I'm sorry, the gold foil experiment.
Rutherford's experiment that determined the size of the nucleus.
All right.
Now, personally, I think I don't believe in electric charge. I think that there's an attraction between the electrons and there's attraction between all elementary particles, just like there is with gravity on our own scale. But my thoughts on gravities are more towards the pushing type of gravity, which explains that how they can the effect of gravity can occur at very small levels like that. But anyway, the results of the gold foil experiment, I think, can be explained by the particles attracting each other rather than repelling each other, because the particles are deflected, and I don't think they can determine whether they're deflected based on opposing forces or attracting forces. I think both types of forces would give the same effect of the alpha particles being deflected as they go through the foil.
Well, actually, that's correct, because they have repeated this experiment using electrons. Okay, so electrons, that would be the opposite charge of that would be negatively charged. But they find that they bounce off the gold foil in a very similar manner to the positively charged helium nucleus is used. I mean, it didn't seem to actually matter what the sign of the charge was. Just to confirm that, it's like it didn't really matter what the charge was. You still get these wide angle deflections.
So I think that kind of just agreed with what they already thought, that there is positive and negative charges, and that the alpha particles were kind of like were being opposed to the gold nuclei, when really it was an attraction, and they were kind of like they got too close and it deflected them, but it wasn't from opposition, it was from attraction.
Could it be too that if there's an attraction thing, it would be like more of the electron slingshots around the nucleus and comes back at various angles?
Yeah, and that's what I think. And also, I think the same thing holds for the alpha particles as well as the electrons, that they're attracted, and I think they slingshot around. And I think everybody believes that it's because they're opposed, the opposite charges, but really they're attracted to the nucleons, and I think it's a slingshot effect for both electrons and alpha particles that are shot through the gold foil.
Well, I would wonder when they do these tests if they can determine whether it's actually being deflected off the surface or slingshotted around the nucleus of an atom, because the distance and time would be very difficult to establish. I'm not privy to the details of those experiments to be able to understand whether or not they could in fact tell whether they went around or not. I mean, if you were to slingshot around something, then you would think that as you move your beam more towards the nucleus, and if they could even control that, then your deflection would be in the opposite direction as you got closer, it would slingshot tight in a tighter format, and you know when you passed the center because it would actually slingshot instead of deflecting. If you were to spray an arrangement of electrons past an object and they were bouncing off, when they hit the object, they would continue to bounce off at an angle to the right. But if they were actually slingshotting around, when you shot to the right, they would come back to the left. I'm not very sure that you can understand that without a picture if I describe that well. But you see what I'm
Yeah,
saying? You should you should be able to
you
tell
can't.
by the angle of deflection and if you know where the nucleus is at.
Well, I mean, I think what the Rutherford's mostly concerned about are these. It's like firing a bullet into a black box, and actually having some of the bullets come back at you, almost 180-degree kind of reflection. So, maybe that might answer some of your ideas, because if it was like a slingshot effect, I don't think it would be able to boomerang back at you. And that's the kind of extremely high angle reflections that you get from these kind of experiments.
Well, it'd be nothing more than like a comet going around the sun. That's coming back at you too.
Yeah, that's possible.
You're saying it couldn't come directly back at you unless it was a total reflection, though. It couldn't come back on the same trajectory it went in at, and I think that's probably true. I couldn't see how you could ever get a parabola to be totally closed like that. So in that case, it almost has to be a reflection if it came straight back.
Yeah, but it would have to be something you would have to try and calculate or predict, because really the only pieces of data that you get from these experiments is just, this is a screen that's wrapped around the experiment, and you see so many particles hit the screen. That's the only thing you really see. It's very kind of crude. There's no detail in that.
Wasn't it more too about how many made it through the screen, though, right? How many hit something and how many went through the screen?
Yeah, the vast majority fly straight through to the end, but we do get some of these extremely high angle reflections. Now, me personally, I feel that the reflections are not due to positive or negative charges, so that would be a completely different standpoint. I, as a physicalist, believe in explaining things like on a billiard table, and the reason why things reflect off of other things is just due to mechanical collision. So I believe that the charge part doesn't really have anything to do with it. It doesn't matter whether you use a positive charge or a negative charge or a neutral charge. If you could do that, you would see the same kind of collision effects. And that's what I'm saying. It's just due to a collision, and that there are just certain parts in the atom which produce these high angle reflections.
So
that would be my opinion.
But it is all about the how many went through is more about what it is than how many, which direction they reflected in.
But according to that theory, Franklin, so what that only particles would only be deflected if they actually came close to enough to the nuclei to actually hit it?
Well, because my atom, once again, I have my model of my atom here, and you can see that if I face it this way, it has a very, very little cross section. And, even if you're going this way, a particle approaching this would only have to go through a single layer in order to pass through it. Now, it's not like these particles are not affected at all when they fly through the gold foil. A thick gold foil, the thickness of a piece of paper, in fact, even a piece of paper will completely stop these particles. So the trick is to explain why is it that like 99% of the particles get through, but some tiny fraction, and it's a tiny fraction, are actually reflected like back at you as a total reflection. So you have to be able to try and explain that. Now, the way that Rutherford explained it was that he took all the charge in the atom, in the gold atom, and concentrated it in such a tiny little speck that you could get a complete reflection. Because that's what he had, that as the electron approaches the atom, it is so repelled that it actually comes backwards. And the only way you can get that kind of reflection is if you concentrate all the positive charges into the core of the atom. So that, I mean, in this case, you know, he's thinking that the incoming particle never actually touches the atom, that it's due specifically due to the repulsion of like charges.
Well, presumably, if the atoms were solid, all of them would be bounced back.
Yes, that would be true. If the atom was,
not all of them are bounced back, very few of them are bounced back, then he concludes that the actual mass, the substance of the atom, is very small compared to the volume that they occupy, which is pretty much what the conclusion is. So I don't really see that you presented any evidence to negate that conclusion.
Well, this is the old, you know, if that were true, then atoms would be 99.9995% empty space. And then the obvious question is why is it my hand just doesn't pass through the wall if all atoms are 99.9995% empty space? That's an illogical contradiction.
I don't think so. I think you just don't know what you're talking about.
Well, then you explain to it, how is it my hand cannot go through the wall if both of these things are 99.9995% empty space?
I'm not the one making the assertion, you are.
Yeah, they're not necessarily empty space. They're just space that's not strong enough in energy content to cause a reflection.
Well, I think the Ray Fleming, maybe it's Ray Fleming or Roger Monday, you may correct me on this, has produces all these, has made a habit of producing these pictures of atoms, and they show the atoms to be like, you know, hexagonal things. That you can actually see them in these pictures that he shows. You know who has done that?
Yeah, that's Roger Monday.
That's Roger Monday. I mean, he's showing that those pictures that the atoms are space filling.
Based on that, one could agree that Franklin is correct, right?
No, because they're using light waves to energy to measure.
So it depends on what you use as your probe, right?
Right. So even the electron, if it's an energy pattern, and that energy pattern reacts with another energy pattern, which would be the rest of the atom, then it could be reflected, because space itself can only contain a certain amount of energy per unit area. And I think it's kind of more that is showing where the density of energy is.
Well, but still, it sort of boils down to what you're using as your probe.
Pretty much, yeah. That's why when they use neutrons, they have a better chance of getting through, because they don't have to go through the electron cloud.
The bottom line is that we get a different picture based on whether we use X-rays or electrons in an electron microscope, or different, you know, obviously if you project a radio wave or a microwave beam against a gold foil, you will get a completely different picture of it than you will if you use a different type of probe, right?
Right. Well, the radio wave and microwave is multiple atoms wide to begin with, so that wouldn't be able to detect, you know, the contents of the atom.
Yeah, but you would get a reflection based on the entire piece of metal, not just it's what's inside of it, right?
Right. And a shorter wavelength you use, the more resolution you get. So, like with pictures that Roger Munn does, the wavelengths they're using are not short enough to detect the details. Whereas if they're using the like a neutron, like they've done in other experiments to the gold foil and that, then the neutron, like I said, can make it through that cloud and is very short in wavelength. It's high in energy, short in wavelength. So if you're measuring something with a very, very short ruler, you can't measure something that's an inch wide with a yard wide ruler and resolve any details. You have to at least have a measurement system that's smaller than the object you're trying to measure to get any kind of accuracy. and that's kind of Roger's thing is they're using photons to measure something that's smaller than a photon. And so all you're really seeing is the nodal points of interference as you move your measurement instrument.
Well, I mean, there's a big difference between experiments where, like Harry says, where you shine a whole beam of something on like billions of atoms and you observe the result and you can see things that way, versus these ultra precision scanning, tunneling microscopy experiments where they can actually image individual atoms. So there is a massive difference in that. I mean, these scanning experiments, are done with. It's amazing they can actually do this. They can actually resolve the atomic position of the atoms, and it's kind of questionable what you're seeing there, because that is, of course, highly dependent upon the software that's being used to interpret the results. Because what they're doing is they're actually, physically moving something, scanning across a surface with like a beam of electrons coming out of the atomic tip, which is only 1 atom wide, and producing these remarkable pictures. But definitely we can resolve the actual positions of atoms. And there was also another recent electron picture about the gold wire that was being strung out, and you could see the position of the individual gold atoms. Now, you couldn't see what the structure of those individual gold atoms, because they still look like, round little balls, as near as we could tell. But still, that's a lot different than the Rutherford experiment, where you're just like spraying a beam of particles against a macroscopic gold foil, and then trying to determine anything about the atomic structure based on that. I mean, personally, it's like, what can you tell about the structure of the individual atom based on that kind of experiment?
Well, you can tell a lot more about it because your energy content of your neutron that you're using is much higher, and therefore your wavelength much shorter, so you can get much higher resolution than you can with any other technique. And that's
but
why
I'm
they
saying
use
that is
So that's actually more accurate. That's taking into account, now you can see the spaces between the electron and proton
that would still be
energy
optical
centers.
kind of thing. I mean, but they're not even actually even using particles. I mean, the way we're doing this is that we're literally scanning a needle point across a surface. So you're not even. It's not like electron microscopy where you're imaging using electrons.
Yeah, but that needle point is still much larger than a neutron.
Well, it
Less.
comes like one atom at the end, and that's what they're scanning back and forth. So I'm still not quite sure how they can do that. That seems kind of inconceivable to me. But yet we have these pictures. That's just how that works. It's pretty remarkable how they do that. But the point is that in Roger's Monday picture, it kind of shows that whatever the atom is, it looks fairly consistent. The atoms appear to have very particular boundaries. And this picture that he always trots out and makes it look very hexagonal. And I have pictures that they've taken of silicon, and the silicon atoms look, very distinct. They have a little bump on the top. They have like a trapezoidal shape, and they appear to have very sharp edges. And that kind of supports the idea that atoms are, in fact, space filling. But we're still getting to the question of, how is it that in the Rutherford experiment, the vast majority of those alpha particles sailed right through, but we still had some of these extremely high angle reflections. So the only way that I can see that working is if you have, is it only very, very certain parts of the atoms are resistant to being passed through. So that's why I picked this model, because here, if you were to fire bullets at this thing, for the most part, it would only have to pass through one layer of Legos. In almost any orientation you could think of, it would only have to pass through one, which is not very thick. But if you were to head straight head on to the axis of this atom, then it would have to go through from here all the way to here. And that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It would have to go through 14 layers of the atom in order to get through if it hit directly on the axis. And that's what I calculate. I mean, I made my own calculations based on, this model to show that, this particular orientation is so rare that it's not going to happen very often. And that I could replicate roughly what was observed in the Rutherford experiment by just doing this simulation of what are all the possible orientations of this atom. So I had mapped out 23 of them. And then you plot what would be the expected reflection rate.
99.999% of the time you would never hit anything when you tried to shoot something?
No, 100% of the time. I would say that 100% of the times you are hitting something, except that you're only hitting through the thin parts of the atom. And that does slow the projectile down. I mean, basically, the projectile will pass straight through this atom at this angle because it's so thin.
It doesn't look like, I don't think I got a 99.999% chance of making it through that arrangement.
Is there any way they can detect if the alpha particle did slow down? That would.
Well, it definitely does slow down. I mean, and if you have a thick enough piece of gold foil, it will stop it completely. I mean, definitely, even though it goes straight ahead, it's slowed down. It definitely has less energy than the original particle.
I don't think I've ever read anything in the Rutherford experiment that said how much energy the particle came out with on the other side. I think that's kind of a guess on your part, don't you think?
It's based on some of the other things I read, but certainly Rutherford himself, they couldn't tell that because all they were looking at were counts of spots on the screen, and that only shows up like a little flash, and on the end where most of the electrons are going, obviously you cannot sit there and count or even guess at what the intensity was.
Yeah, because the speed of a neutron it's undetectable until it strikes something and causes an electrical interaction.
But these kinds of experiments
can't be detected. It's hard to detect what speed it was going at.
Well, currently, I believe, this is where you read where they do other experiments like this. I mean, they use this kind of experiment for other things, for materials analysis, and then in those experiments they do measure what the energy of the outgoing particle is, and it is less, and it gets significantly less as the material gets thicker until it reaches zero. I mean, that's only logical, right? That it doesn't pass through.
I don't know.
There was nothing
might be
there.
Logical. I don't think I've ever seen results indicating that. But if you've seen some experiments, maybe you can share them with us.
No, I think that's probably what I've seen. That it does slow down. I mean, if it didn't slow down at all, then this particle should be able to go through like a foot of gold and never stop. I mean, why would it stop?
Well, if it did slow down, it would be like your in a statement that things can, like inertia going through your ether, the ether would collapse behind it and reaccelerate it, so it wouldn't slow down. So why would it be any different for the atoms? If you go by that.
The thing is that this is my thickness thing, because if you had a gold foil the thickness of a piece of paper, those alpha particles would be stopped completely. Right? That's enough to stop the alpha particles completely, right? Now, in order for them to be stopped at all, they would have to be at some point slowed down, right? So the fact that a gold foil the thickness of a piece of paper is sufficient to stop the alpha particle completely would logically indicate that at some point they had to slow down, because obviously they reach zero velocity in the, you know, paper thin gold foil.
Now, if that is true, that a lot of them do actually slow down, that would support your theory.
Yeah, I think that would. I mean, I would certainly predict that because the gold foil, the only reason why I was using this gold foil is because it's the thinnest possible metal you can make due to its malleability. But even so, it's still probably a couple hundred atoms deep, right? But that would be thin enough so that the electrons still have enough kinetic energy to pass by most of the atoms that are there, however you think they're formulated. But like I said, the most difficult thing to explain is, you know, why is it you get these high angle, like literally reflections? You know, that's the thing that Rutherford remarked about, that he thought that it was like firing a cannonball at a tissue paper and having it come back at you, right? This is his surprise. I believe that's a quote from him to explain, you know, why that is, right? So, you know, his explanation was that, okay, well, we just put a gigantic opposite charge on the tissue paper and it will cause the cannonball to come right back, right? Oh, but you know, my alternate explanation to that is to say that there's just certain orientations of the atom which are highly reflective. And now, one of the predictions of, say, my theory that could be testable is that instead of using randomly oriented gold foil, that if you could somehow create like a crystalline sheet of gold where all the atoms are exactly aligned in the same direction, that you would find that the reflection rate would vary dramatically depending on the orientation that the beam is incident to the experiment. So if this were the gold sheet and you oriented it specifically right at the polar axes of the atom, then you would see the high reflection rate increase dramatically, versus this way, in which case you'd see the high reflection rate be practically zero. So that is, you know, a possible experiment that someone could do to either confirm or deny this particular hypothesis about the atom being this particular geometry, you know.
If they could do that, that would support your theory. Another thing I'm not sure if they can do this or not, but I was kind of thinking if they could slow down the alpha particles when they shoot them at the gold foil. Now, if some of the alpha particles don't come back or are not detected at all, then that might support my theory by the alpha particles actually being attracted right into the nucleus and being caught in the nucleus, because according to the normal theory, where they oppose each other, you would think that even if they were going slowly, they should always either be deflected or still go right through. They should always be detected somehow.
Yeah, I think that may be something that we are now technologically capable of doing. You may be able to at least sort, because back then all I had was like a radium source, and that was the only source of. I mean, this experiment was done like over 100 years ago, and they barely even knew what radioactivity was. But now we can probably make our own custom helium nucleuses with practically any energy we want. And these accelerators, I mean, that's what they start out with in CERN, I think. They have these, they have like this little tank of hydrogen, and that's where all of the collisions start, right? I think they can probably accelerate anything, but you would predict that because you're thinking that the the particles are actually attracted to each other, although I still find that a little bit hard to understand because the alpha particles are positively charged, and the atom, the nucleus at least, is currently thought to be positively charged. So I'm not quite sure if I understand why you would think they would be attracted.
I don't believe in charge. I know that.
Don't believe in charge.
Right.
Actually, that's more interesting than the other part of the discussion. Why don't you believe in charge? What do you mean by that?
Well, I don't believe. I think charge is something that was thought up back in the 1800s when we knew very little, and we made a lot of assumptions. And if I remember right, I think Ben Franklin was maybe a big proponent of electronic charge to explain different phenomena. But I believe that alpha, or that elementary particles are, I guess my theory is kind of like, I call it the astroatomic theory, where I believe elementary particles are attracted to each other just like planets and all of our stellar particles are attracted to each other, except on a tiny scale, in that everything that we observe as far as magnetic interactions and electrical interactions can be explained by attractive forces rather than the forces being opposing. And I guess this is where I started out with the gold foil experiment, because it was one of the first things that everybody thought, well, this shows that there are attractive forces. Well, I says, well, are opposing forces, and I thought, no, it could still be explained by attractive forces. And I know that I'm not the only one that believes this theory. Glenn Burchard also kind of believes this, and I've also seen some videos on the dissident scientists on the same subject, which they don't also believe in in electronic charge.
So how do you explain the classic electrostatic experiments where you get two pith balls and you charge both of them up negatively, and when you try and put them together, they mysteriously run away from each other?
That's a good question, and this is explained in, I forget his name, but he did experiments where in water, where he would have two, I'm not sure what they were, like barrels rotating in the same direction, and they would oppose, but if you rotate them in opposite direction, they would attract each other. Some of you might be familiar with that experiment. I'll have to find out who did that. But that would explain why some things attract and repel each other. It's because of the dynamics of their rotation in respect to each other.
That's kind of an explanation for charge, but it's not really getting rid of the concept of charge. Yeah, I'm still having a hard time seeing, well, you've got a positively charged alpha particle, and that's just basically helium with both of its electrons stripped off. And it's approaching a gold atom that has, I don't know, what was it, like 93 or something protons in it. That, even by any explanation of charge, rotation or not, I mean, both of those are going to be like rotating in their opposite directions or whatnot, one would still predict that they're going to go away from each other. They're going to run away from each other. They're not going to be attracted.
Yeah, the rotating effect plays no effect there. It's basically what Cornelius had said earlier. It's the slingshot effect that explains that. That some alpha particles pass through close enough to one of the nuclei where it's slingshotted around and comes back.
Mm-hmm. So, Harry, what do you think of that?
I'm not sure what aspect of it are you referring to? I'm not a big fan of the concept of charge because I think it's a misleading idea. Um, you sort of have to pin down what it means, but to go back to what he was saying, the idea comes from the idea of charging a gun. In other words, you would charge a Leyden jar, you put charge into it. So the idea was that electricity was a something, and that you would to charge a Leyden jar with electricity, whatever electricity is, assuming it's a something. So you would charge the Leyden jar with electricity like you would put a charge of powder in a gun. That's kind of where the concept comes from. And then it kind of became an idea of that charge is a something, but what this something is isn't really clear. So I'm not really a big fan of the word charge. I think it's more a property or a description than it is something or an entity. Does that help you any?
Yeah, that's interesting. I wouldn't mind hearing a little bit more about that sometime.
Yeah, charge as charge in a gun, I think, or charge in a bullet, because that is kind of an interesting concept that we
Well, it's more the idea that you're charging like you put a charge in a cannon. I think that's where the idea comes from, that you're putting something into it. And so, but the idea of charge, and to a certain extent, what charge is, if you really want to get down to it, it's really a measure of the quantity of electric field.
yeah, there's this thing that comes off of these charged objects. We call that the charge field. So if I get my Van de Graaff generator and I, start running that thing, then if I touch things to the dome, what we think is happening is that, well, first we see the charge transfer. It's like, just like the bullet being filled with gunpowder, it gets whatever this thing we're calling charge, it gets to the pith ball. And then if we go and we charge another pith ball with the same charge, then we can see that those things seem to repel each other. But if we got a Van de Graaff generator that generates the opposite charge, and we charge the pith balls, we see them do this attracting thing. So there seems to be this polarity. Now, mainstream would explain this as actually a change in the number of electrons present. So if I take an object and I push more electrons into it than it would normally naturally take, then we would say that that is negatively charged. And then if I took an object and I sucked out the electrons, then we would get something that we would call positively charged. That is, I believe, the mainstream interpretation of what's going on with what we call charge.
Ben Franklin theory.
Yeah, I think that's probably Ben Franklin came up with. He thought of electricity as literally a type of fluid.
Right.
That flowed from one place to the other.
If you had too much of the fluid of electricity, you had plus charge. And if you had a deficit of the electric fluid, you had negative charge. That was the Ben Franklin theory.
Yep, and that was the Ben Franklin theory.
And I think that kind of led us astray too, because I don't believe that the concept of charge, even in regular science, has anything to do with a surplus of electrons and a deficiency of electrons.
Well, we do see. I mean, we can get fairly precise these days. Like we can track a single electron going through, say, electric field, and you can track these things in like cloud chambers or whatnot. And you can see, depending on what we think the charge of that individual particle, like an individual electron, we can see go make a track through these things. And if you put a positive side on one thing and a negative charge on the other, you'll see it deflecting away from the negatively charged side. So that to me tells me that charge is a property of the subatomic particles here.
but again, the deflection can be or can be described by other factors too. And also, have you ever done experiments with charging a small object and actually seeing? I don't know if they have instruments that can do that, but seeing if it actually weighs more or has more mass than a negative charged object, which has basically the same except a negative charge.
Well, you think that'd be possible because now basically we're talking about an ionized. I mean, you should be able to take the mass of an ionized atom versus a non-ionized atom, right? So ionized atom is just an atom that has its electrons removed, so it should be positive.
Well,
although I can't specifically cite them actually doing that and showing that it is in fact the mass of 2 electrons or whatever less than the one that. I mean, I would think it would have to be, right? It's
yeah, I can't recall either. What was that, Harry? Did you mention something also?
This is an old idea that's been around for quite a while. I think it's probably been refuted by experiments, but I don't know of any. It used to be thought that a magnet negated gravity when that's how magnets work. In other words, if you held a magnet above a piece of iron and it would lift the piece of iron up, that it acted by negating gravity of the iron. But that's not really the modern view of it.
Yeah, I would totally agree with that. It's like the magnet has its own attractive properties. But
I think the problem here, of course, the real problem or the issue is that I don't think anybody really knows what gravity is. I don't think anybody knows what electric attraction or magnetic attraction is. And that's kind of a difficulty. So we have to sort of live with the fact that we don't know what those things actually are. And I think Newton talked about that when he said, what is it, hypothesis non fingo? Wasn't that what he said? I make no hypothesis, meaning he didn't really try to explain what gravity is. He was merely describing it.
Yes, I mean, I think that would be totally true, that from a mainstream's perspective, we don't know what gravity is, we don't know what charge is, we don't know what magnetism is. So my question is, how can we claim to know anything if we don't know the basis of these very fundamental forces? I mean, we seemingly just be sitting here like a bunch of ignoramuses cavemen. Even in spite of the fact we can build things like the LHC, but
on empiricism, and so you even if you don't know what gravity is, and gravity might be more described as a property, and who knows whether it's a thing or just a description of events. But if you lift a book off of the desk and then let go of it, it will fall to the floor. So we know it will fall to the floor. I don't know that anybody disputes that. So we do know that.
Okay, I'll give you that. So certainly we know the empirical properties of these forces. So I guess we do know something. It's just, so we're not quite as ignorant as I might claim that we don't know anything. But still, we're kind of ignorant about what these things are. It's like, Lisa Randall was asked point blank, what is charge? And she actually gave the honest answer, which was, we don't know. So that is the honest answer.
Well, it depends on what level you mean by we don't know. I would define charge as a quantity measure of electric field. So you can sort of, there's a way in electromagnetic theory that you can define what charge is. And it has a definite meaning, and you can measure it and assign a quantity to it. Okay. But to know, that's one form of knowing. The form of knowing of what is charge in a philosophical sense, or what fundamentally does it mean, or what's the mechanism by which charge operates in a more fundamental thing, that's really we don't really know that. So all we can say is charge is a property and we can measure it and assign, polarity to it. How it creates attraction and repulsion is kind of, there's a mainstream theory. They have a theory about exchanging photons and that sort of thing. And so there's theories and models that can be used to describe it, but I don't know that you can philosophically identify its essence, if you will.
Yeah, you mentioned that they have this photon exchange is how they generally describe it.
But that's in quantum electrodynamics, remember now.
It always ends up like, on the Channel 9, the PBS specials, like Brian Greene, they showed like two people like throwing a ball at each other, and the faster they throw the ball at each other, the more they're attracted, which seems completely absurd.
It doesn't make any sense to me, that's for sure.
But that is how they explain it.
Not a new idea. This goes back to the Greeks. The Greeks had tried this theory, and the idea was that magnetism. The Greeks didn't really. Electricity wasn't really well understood. Well understood is kind of like vague, but magnetism. There were actually theories of magnetism in the Greek period, if you read my paper and on this. And the idea was that magnetism was a form of particles, and these particles moved back and forth between the magnets and the iron that was attracted by the magnet. And so that idea of these particles being the mediator, the what mediates the field, the field being a modern idea, that idea is pretty old. So mainstream is really basically kind of recycled an old idea.
Yeah, I just showed it. There's a thread going on this week about gravity and its relationship to, say, the electrostatic force and or electromagnetic waves. So let's see, who is this? So Mainframe. So he comes up with some interesting points here. It says gravity is self-similar to electrostatic force, but they are not the same. He says the electric force is far stronger than the gravity force. Their self-similarity implies similar deterministic mechanism is in play, but one would give different strength magnitudes for each. So he's trying to relate gravity to the electrostatic force. And that was something that Einstein was trying to do up until his dying days, but could never do. So he says the general relativity conundrum equations reveal distortions on the fabric of space. Space-time continue that lead to gravity being produced. So what causes distortions in the continuum? Density change. What causes density change in the fabric of space? So this is more going along Einstein's thing. So in a material that can be mathematically defined by continuum physics, the displacement of the constituents, that continuum medium. So what are the constituents of the continuum medium, the vacuous space in which different strengths in different differentials can result in both forces of the magnitude of the electrostatic force and the gravity force? One medium cannot. There are two mediums, two spatial mediums where collectively they are one. You have a gravitational space-time medium and electrostatic medium, both intermixed. But what are their constituents? Whatever constituents are, they are self-similar. And how can they be displaced to change the densities of each continuum medium? There are many ways to displace the density of a material structure made of constituent parts. So what do you think of that? Are there two mediums, one for electrostatic and one for gravity, but that they work the same?
Well, Bill Lucas says that gravity is a electromagnetic interaction. So he has a different idea on that. This is Robert DeMello, if I'm not mistaken, and I never really could understand anything he said, so that would be my comment. It's ununderstandable to me.
Well, there are a couple of arguments going on here. So,
Well,
I kind of
I
had to
think
drop out.
the real problem with gravity is that it's very difficult to do an experiment with gravity because it's such a small force, and it's very difficult to do experiments in the laboratory. So we're sort of trapped into um, um, looking at planetary systems and stellar systems and applying what we think are the laws of gravity to those systems and then seeing whether or not our theory works out. And that's kind of a limiting, um, that's kind of limited. In the case of electricity, um, it's actually a little bit easier about the attraction. And what we know is that if you look at capacitors and the forces, it turns out that when the plates of a capacitor, if you will, or the two charges, the plus charge and the minus charge, when they move towards each other, the potential between the two plates decreases. And so there's a relation there that says that the total energy, it looks like the total energy is decreasing. So what happens is that the dynamically, when attraction occurs, there is a decline in energy of the system. And then when, for instance, if you want to charge create in these electric machines, these Wimshurst machines, you're familiar with these machines, they basically convert electric mechanical energy into electrostatic energy by pulling the charges apart. So what happens is when you pull a positive plate, when you separate a positive charge and a negative charge, you use mechanical energy to do that. So we know that certain things about electricity that how the energy relations work there, and that's not really as easily well defined in the case of gravity. Did that help you any?
Yeah, I can agree with that.
well, I have a hang up about this thing about saying that gravity is a weaker force because I would challenge you to lift me over your head and continue to assert that gravity is a weak force because it seems to me that gravity on the Earth is, in fact, a very strong force. And this whole strength argument is kind of bogus because it's all relative, right? It's like if I have a bottle of dye and I take one drop of
Well,
that and I stick that into my bathtub.
If I in the macroscopic world, I mean, if you take a comb and you rub it, okay, and charge it up, and then you start attracting bits and pieces of things, they actually will move up towards the comb. So that says that the force of the electricity in the comb is greater than the force of gravity that's pulling the objects down, don't you think?
Well, it's a strength per unit mass argument. It's like if you had a pound of electrons and you measured the electrostatic force coming out of that, it's like, yeah, that's going to be a lot stronger than a pound of like dirt, right? With the pound of dirt, the gravity force coming out of the pound of dirt is going to be a lot less than the pound of electrons. But if you just took your pound of electrons and instead just took like 5 of those electrons and stuck them into the dirt, then do you still not have, I mean, the force would be very much weaker, but would you claim that that's a fundamentally different force or just a diluted force? Do you understand? I'm saying that they're only saying that it's basically on a force per unit mass basis that it's weaker.
Well,
but
if you're Bill Lucas,
do the same thing.
If you're Bill Lucas, then you can sort of say that gravity is a sort of a residual of the electrostatic force.
Yes. I think that's what he would definitely say.
And so from Bill Lucas's perspective, the gravitational force is a sort of a residual force that's left over. And so so the fact that gravity is much weaker allows him to say that.
Yeah, I would say that's weaker because it's kind of a residual. I would say more diluted effect, but I think residual is also a good way of saying it. But
Well,
that,
it's just, I don't know. Bill would have to defend what he says. I mean, I'm just sort of characterizing it briefly here.
but that's kind of going towards the idea that gravity is some kind of aspect of the electrostatic force. It's just like
Well,
I said, it could be
like
diluted.
just like to unify all the forces so they can explain things with the least or fewest basic starting principles as a starting point.
Yeah, so I mean, I think the goal would be to, because we have these things, charge, gravity, magnetism. I think it would be great if we could unite all of those as being an aspect of one of those forces, right? So maybe everything's magnetism. Some people like to say that. Or maybe everything is gravity. Or maybe everything is the electrostatic force. So I think that, that would be a worthy goal, to take these three and say that the other two are some kind of geometric variant of the other, right?
I also think density. I'm sorry, Cornelius. Go ahead.
No, that's pretty much the aspect that I've taken. I mean, it already is. One is basically nothing more than the geometry of the other, and there is just. You asked earlier about, and I missed the part about where you were talking about the different two different carriers or two different fields, but I consistently say that there's just one field and just one carrier, and there's a difference between the transverse and longitudinal energy patterns or waves that go through those that constitute what makes gravity and what makes electrical charge and that. And, so there's one carrier and one form of energy that when geometrically manipulated, the others arise from. Bill also has not just it has a transverse and longitudinal characteristic in his model. I would differ with Bill when he says that gravity is electromagnetic or left over from the electromagnetic. I think gravity is a characteristic of longitudinal waves, which he calls basically, I think, the life force waves or something like that, where you can get a life force meter in that. Uh, and so I have gravity as part of that geometry of waves, and electromagnetics is on top of that with transverse characteristics or distortions of those waves. So, but it all combines in one field.
So what is the fundamental field? It sounds like that your fundamental field is neither gravity, charge, or magnetism.
No, gravity, charge, and magnetism are all geometries of tension waves within a tensionable media. That's all I've got. I mean, I don't have anything more fundamental than that. I've already described
So in
before
that
to
case, they
people.
all kind of take the same footing, that they're all spring from the same root.
They all have the same substrate. They have
Yeah,
one
okay.
substrate in which that substrate is capable of supporting both longitudinal and transverse wave varieties, and that the tension within that substrate determines how fast those varieties move, and which variety moves faster than the other, and how much density there can be in those wave patterns. Because when you get towards an atomic pattern, the waves become very dense, and the media's tensionability becomes very weak.
Well, I think it's a worthy goal to have a single medium, rather than try and say there's separate mediums for everything, because I think other people do that too, is that they'll say, oh, there's a separate medium for the charge field, there's a separate medium for the gravity, and there's a separate medium for the magnetic, right? And that seems kind of complicated. So it would be better if we could come up with a singular medium that can support all three of those things at the same time.
Well, I think it's well accepted now that electricity and magnetism are unified, and so they're not really separate. Although the problem I have is every time I hear this business about photons and photons mediating the electric and the magnetic force, I ask, well, what's the difference between an electric photon and a magnetic photon? And nobody seems to be able to answer that one. So I agree that's kind of confusing. How can you say they're unified, but there doesn't seem to be a difference? But
Yep.
the issue of magnetism and electricity are clearly unified in electromagnetic theory.
Well, I think in
Yeah.
the sense that empirically, we know if you have, such a electric situation that it just creates this magnetic situation. I think that's kind of an empirical understanding, but still not, I would say, basic, how does this work explanation.
Yeah, I never really use
How,
the
but
term
not really
electric and
why,
magnetic.
right?
I would never
You
use
know,
the term electric and magnetic separately because they're always combined. One is just a different aspect of the other.
Correct.
I mean, you asked that interesting question about how is it they can possibly say that charge is mediated by these photons, and then say that that because there's this difference. You have the electrostatic attraction, and then we have these things. Then we also have electromagnetic waves. That's another whole topic. So electromagnetic waves don't seem to have anything to do with attraction, but yet those are the photons that they're talking about, right? So photons are these electromagnetic waves so far as mainstream is concerned, right? Would you agree with that, Harry?
It's a model that they use, which kind of depends on, I don't know. You got to be careful now about, if you're talking about, like, say, for instance, quantum electrodynamics, that's where they use the word photon as being the object that's mediating the field force.
Well, I
I
mean,
think
That's a particular theory.
the way that I attempt to unify that is by saying that let's say the positive charge and negative charge, they do emit photons. I say that they ring at their resonant frequency that generates electromagnetic waves, and those are what mainstream calls photons. So in that way, and the photons are in opposite phases, and then that creates the attractive forces. So in some ways, I would have to agree with the mainstream that the thing that is causing the attraction are the photons. The photons are in opposite charges cancel, creating the negative pressure, and that causes an attraction. Or between two similar charges, those are emitting photons of the same phase, causing regions of high pressure between them that causes repulsion. So, I mean, that's a much different picture than the two people throwing balls at each other, and if they throw it faster, they attract each other, because that's just nonsense. But if you think of them exchanging waves, like they're firing wave cannons at each other, and the way their waves interact, they either push the people apart, or the outside forces are pushing them together.
Yeah, but it's not really
kind of
clear
thing.
exactly how they make no distinction between the photons emitted by the negative charge and the photons emitted by the positive charge, or the photons emitted by a magnet positive pole or the negative pole of the magnet. So, I mean, I don't, none of that really makes much sense.
Well, that's where you have to start postulating a couple things. Like I said, the only distinction I think there is between the positive electric field and the negative electric field is a matter of phase. That is, if we think the electrostatic charge field itself is made out of electromagnetic waves. So there's a couple of things you'd have to swallow there. One, that the electrostatic field is just an electrostatic wave coming out of the particle. And two, that those things can interact in such a way that it causes these particles to be attracted or repelled based on those interactions. But that's one way. That's one way to explain, this idea that charge arises due to photon exchange.
That's fundamentally agreeable, except for the electric charge itself is a wave pattern. It's not, as opposed to, and the particle is basically a captured wave pattern. The photon is a wave pattern as well, but the reason they call it and they call it what they describe as a photon is, and I think you said that too before, Franklin, is it's a wave packet. It's a burst of waves or a pulse of waves, instead as opposed to a continuous pattern of waves. So they say we have this wave grouping, which is we're going to call a photon, and that wave grouping can come in various lengths of waves, and the length of wave determines the light color. The electric charge and positive electric charges, the positive and negative electric charges, are basically photons that are captured by a pattern of mass, because any electric charge, whether it be a positive charge or a negative charge, always has a mass associated with it.
Yeah, I mean, all of that is true. I mean, but what I'm trying to do is trying to unify. So, I mean, your goals are to take charge, magnetism, and gravity and try to unify them under something. Now, I prefer to try and unify them to one force. So I will take gravity, charge, and magnetism, and I will say that I like the electrostatic force to be the fundamental. So I should be able to build gravity and magnetism out of the electrostatic force, out of just a force between positive and negative charges.
And I prefer to use just tension force and build all three out of tension.
Yes, and so that's another approach where you build all three kind of on the same basis, out of the same fundamental medium. Whereas my approach would be to take the electrostatic force and then build gravity out of that. So the way I do that is I just say that that gravity is just a direct aspect of the electrostatic force, that the Earth is a positively charged ball, and all neutrally charged matter, which is everything, is attracted to the surface of that charged ball. So that would be a direct unification of the electrostatic force with the gravity force.
Yeah, but the moon is also a positively charged ball.
That's right. The moon is also a positively charged ball. The Earth is a positively charged
charges now that repel each other.
Positively charged ball. Every single planetary object in the universe actually contains net positive charge.
Which means everything flies apart because it's all positive.
Nope, that's not true, because the thing is that all the neutral matter in the Earth, which is 99.99999% is attracted to the positive charge of the sun. So it's actually gravity.
That only is true because the negative charge in that neutral matter moves to the opposite side, which means that anything on the opposite side of the Earth would have a strong positive charge, which means that there would be repulsion to anything on the opposite side of the Earth. So if that would be
presuming that there's a migration of charges, but what I'm saying is that in the individual
not a presumption. That's the way experiments show. That's the way.
Your charges are not that mobile. What experiments show, but it's science is that everything is made out of dipoles, and as soon as you put it in an electric field, the dipoles will align. They'll point at the center of the charge. And so one of the experimental things that I claim that you could do, that if you can measure the dipole orientation of matter sitting on the Earth, and we should be able to do this actually, you would find that they're all pointing to the center of the Earth.
They can't.
That is an experimental.
Because that would mean all the negatives were pointed towards the center, which would be to repel, and they immediately switch to becoming the positives. You can't.
No.
your dielectric material can only occur in a plane. It can't occur in a sphere.
No. What you have is you have a positively charged ball. You put neutrally charged matter on it. The dipoles in the neutral matter will be oriented towards the positive. You know what a dipole is. It's got a positive, it's got a negative end. So instead of being randomly oriented, the negative ends of those dipoles is going to point towards the center of the Earth. They're not going to actually physically migrate down because that would cause a separation of charges. Charges cannot separate. There would be no separation of charge. It's not like one side of the Earth is going to be negatively charged and the other side is going to be positively charged. That's not going to happen because it might happen if the Earth was a steel ball, was a perfect conductor, maybe. But
so lightning doesn't happen.
No, lightning happens, and that's actually a direct consequence.
The separation of charges.
That's due to the separation of charges because the Earth is typically positively charged, and the clouds, due to separation of charges, would become negatively charged. I mean, that is one instance where the separation of charges, but the separation, say, your body doesn't happen.
Sure it does. If I approach a positive charge, my negative charges will be attracted to it on one side of my body, and the opposite side of my body will become more negatively charged. I'm a dielectric just like anything else.
Yes, but to a limited degree. But in any case, that doesn't. The thing is that the neutral matter in the Earth is going to be attracted to the positive charge of the sun. And the neutral matter in the moon is going to be attracted to the central positive charge of the Earth. So what gravity is, in my opinion, is a balance between those two. Yes, you have the repulsion of the net positive charges between the Earth and, say, the moon. It doesn't fly away because they have still the attractive, it's called a dipole attraction.
Mm-hmm.
It's given the scientific term of diphoresis, and that is something like a 1 over r over 3 force versus a 1 over r squared electrostatic force. And in my opinion, those two things balance out. But it also means a couple of things, that like the gravity constant wouldn't actually be constant. That it's possible that the moon could have a different fraction of charge versus the Earth versus Venus versus Mars. That if we were to, now it might be very close, because just from the equilibrium standpoint, that you stick anything into space, it will reach an equilibrium point where so many electrons are stripped off until it can't support it anymore. And that's what we generally see throughout the universe, that it's the same fraction is going to be ripped off. But I was just trying to explain to you, why is it if the moon and the sun are both positively charged, why they do not fly apart? Because there is an opposing attractive force.
Yeah.
That's how I unite electrostatic and gravity.
I appreciate the effort, but I'll stick by what I said.
Yep, you can stick by what you said, but that's one way of doing it. So, and then I have to unite the electrostatic with magnetism. So I'm saying that magnetism, in fact, is an electrostatic attraction of also opposite. But fundamentally, when you put a north against a south pole, you're fundamentally looking at an attraction of opposite charges. Now, the only way to explain that is to say that the electrons in the pieces of metal, like pieces of steel, are actually being deflected towards each other. So we know if we stick an electron between a positive and negative plate, we get a deflection of that electron. Now, effectively, that is what I believe the magnetic field is that the magnetic field sets up a situation where the electrons in the atoms, they're moving around in these current loops. And I believe they're superconducting, so there's always electrons moving in magnetic material. That those electrons are being deflected, say, towards the other magnet that's doing the attraction. So in that case, magnetism can be said to be an aspect of the electrostatic force. It's a highly geometrical, mechanical construction but that's one way of doing it.
Magnetism is due to electrodynamics, not electrostatics. You can
No,
bring
that's
a
what
magnet up.
that's what I'm
You can bring
disagreeing with.
You can bring a magnet up to next to a Van de Graaff generator that's electrostatically charged, and it won't care whether it's charged or not. It'll have just the same degree of repulsion and attraction to it. And
Yeah, that's right. Because actually,
I don't care if you bring the North Pole closer or the South Pole closer or both poles closer. That magnet will not be able to detect whether that Van de Graaff generator is charged or uncharged.
yes, and I totally agree with that. That's
So it's
because
not electrostatic, it's electrodynamic.
no, I can't totally
The
explain it
electrons
in
have
terms
to,
of
the
an
electrons have to be,
electrostatic force.
the electrons have to be moving to create a magnetic field.
Absolutely. No, the question is, see, the thing is that the magnetic field is an aspect of the ether.
If the electrons are moving, it's no longer electrostatic, it's electrodynamics. And you said absolutely just now.
Electrostatic in the sense that it's an attraction of opposite charges.
It's electrodynamic in the sense that those charges are moving.
Yes, they're still moving, but they're still under the influence of electrostatic. I mean, call it electrodynamic, electrostatic. Don't get your axles wrapped around definitions here.
No, we have to get our axle wrapped around definition because electrodynamics gives polarity, electrostatic does not.
What? Electrostatic
is electrodynamics that gives the polarity to the magnet, because the magnet is polarized based on the direction the electrons are moving.
Yes, and the electrostatic is polarized depending on what charge you have, so they're both polarized.
It doesn't matter which charge you have. If you're moving electrons one direction or the other, it determines whether or not you're getting which direction the magnet's polarized. You don't need protons to move it whatsoever. You can or you can move positive charges, but you don't need negative and positive charges to create a magnet. You need one or the other charge type moving.
Yes. Now you would have to actually read my paper on magnetism to understand that.
No, I don't think I do. I don't think I do. I work in electromagnetism.
Well, I'm sure you do, but you should probably look at it because there's a possible explanation for how that actually works. But it requires a medium, a polarizable medium, in order to make those actions happen.
No, it doesn't.
Well, that's what I'm arguing, is that magnetism is an electrostatic force, and it's due to a polarization of the actual medium.
The polarization is due to the motion of the waves, the direction of the motion of waves through it.
Well, I would, once again, we all have different ideas, but once again, I can only explain what I think. So I think that that magnetism can be explained in terms of just attraction of opposite charges. Gravity can be explained in terms of attraction of opposite charges. And the electrostatic force, then you still have to explain that, which is why is it a positron attracts an electron? And I explained that, as I said, as like a photon exchange of opposite phases. So in that way, that's why I like my picture, because with a single starting point of just the electrostatic force being a wave in this medium, and the medium is being made out of matter particles we can recognize, which is positrons and electrons, that we can explain the electrostatic force and the gravitational force and the magnetic force as being all aspects of the singular force, electrostatic force, in a singular medium. So that's why I like that particular explanation, because we can unify all these things under a singular medium and not give gravity a different medium and electrostatics a different medium and magnetism a different medium. The goal should be to unify all these forces as the same thing under a singular medium. So that's, and we're definitely not there in mainstream right now. We definitely have all kinds of, we don't know how this works kind of thing. So, but that's why we're here to discuss these things, see what's possible. So, and if people don't like that idea, then they can tell me why. That's perfectly fine. I mean, I may not be right, but I'm just trying to find the singular thread that answers all the questions. But it looks like we're getting towards the end of our discussion here. So let's see. Let's kind of summarize what we were going through here. So we were discussing. We started getting into atomic physics. Now Harry is very tired of us discussing atomic physics. So we tried to go and find out, what, because he thinks everything has been tried and done. It's all explained, that there's no point in exploring atomic physics because everybody knows everything there is to know. But, I would disagree. I think there's still a lot of internal self-contradictions in the atomic model. And so I brought up the article showing that that the nuclei basically follow the electrons around when they in this experiment there. And that was surprising. That was a surprising result for the researchers, who would think that the electron should be much freer to move around versus the much heavier nuclei. And I personally think that that's a very interesting result. I think it is perfectly valid to look at the results even in these news articles. I think Harry would disagree, but it's like, I think that's a perfectly interesting thing for us to take a look at, because this supports the idea that let's say the electron is actually glued onto the proton and it really can't get away from the proton. So yeah, it drags it around, versus the expectations of the mainstream model, which may be wrong. And then we discussed, where did the mainstream get their ideas from? We discussed the Rutherford experiment, which has been used to justify that all the protons are locked into this tiny little ball in the nucleus that cause these alpha particles to directly be reflected back in the Rutherford experiment. And we had some discussions about are they like just being deflected going around? Are they attracted? And even the question of whether there's even charge there. I mean, so I think Mitch was saying that he doesn't believe that there are charges, so therefore the incoming particle is actually attracted to the atom and not repelled by it. And that was kind of you can kind of justify that, because it didn't seemingly didn't matter what the sign of the charge is in order to get these results. So we're trying to explain how can you explain these results. So as an atomic modeler myself, of course, I would try out my model, which tries to explain why is it that most all of the beams go straight through the gold foil, but some come right back at you. So we tried to explain that result, and we looked at the atomic pictures, which show that it looks like the atoms appear to be something space-filling, solid, taking up like 99% of the available space, and that's why I cannot put my hand through the wall, because all my atoms in my hand are 100% space-filling, as well as the atoms in the wall. Therefore, they cannot get past each other. So this idea that the atoms are 99.9% empty space just doesn't seem to be right. And let's see, what else did we get into? Then we started getting to the details of charge, and Harry brings up the point that we really don't know what these three things are: charge, magnetism, gravity. Einstein tried to unite gravity with electrostatics, and he failed, right? So why did he fail? Perhaps he was looking too hard at the subject. So then I tried to explain my own ideas about, and Cornelius described his ideas. He thinks that these three things actually spring out of basically the same material structure. So they kind of have the same aspects of the fundamental medium versus say my theory, which I think everything springs out of the electrostatic force, and that we have this idea that there are photon exchange particles that cause the attraction for charges, which is the closest thing that mainstream can say. And I tried to explain that they might actually be photons, and that it's the only difference between the photons being exchanged is a matter of phase. so that the opposite photons cancel and the similar photons add, and this is what causes the observed attraction and repulsion. So maybe that's not as crazy as what would first seem. So, and I think that brought us to the end of the discussion here. So if you guys want to talk about something other than atomic physics, because Harry is totally sick of it, and I would agree, we need to find a different topic to talk about. So I will come up with something, but as your homework, you guys see if there's something that you want to talk about. Earlier, before the discussion, we were talking perhaps things like climate change, which would be completely different. But something other than atoms or gravity and charge. Let's see if we can come up with a topic that's a little bit different than either of those two. All right, so that will do it for this week's episode of the Science Chat, and hopefully we'll see you next week. Same time, same place.